Okay, we're going on further in Chapter 7. And if you remember, a joule is a Newton meter or a kilogram meter squared per second. So that will become important later. But we're going to start exploring more quantum behavior. So particles do have wave-like behavior, and that's described here by what's known as the de Broglie wavelength. The Broglie wavelength is the Planck's constant over its momentum. Mass times velocity is momentum. So what is the wavelength of an electron traveling at 2.65 times 10 to the 6 meters per second? That's pretty fast. 2.5 kilometers a second. Whew. It's flying by. Not even close to the speed of light, though. So that's about 1/100th of the speed of light. So we're still not even at the speed of light yet. But electrons are pretty easy to speed up real fast. Cathode ray tube TVs did this. You run electrons through a wire, a lot of intensity, electrons will pop off, and then you have plates that you put in at negative charge, and you can shoot them along the line. That's what an electron gun does, and creates cathode rays. That's a cathode ray, and then the electrons would bend, and then they would hit a series of pixelated, they're usually hexagonal things, and where the electrons hit, for a color TV, it would be one of 3 colors. For a black and white TV, it would be yes or no color, and then you would have that on a screen. So now we have liquid crystal displays where it's actually little dots, little pixels. So and the liquid crystals have the different colors. But the old school TVs, that's how they worked, kind of off of this idea. Okay, de Broglie wavelength is Planck's constant over mass times velocity, and the mass of electron is 9.11 times 10 to the minus 31 kilograms. So the Broglie wavelength H6.626 times 10 to the minus 34 joule times second, all over mass 9.11 times 10 to the minus 31 kilograms, and velocity see here, 2.65 times 10 to the 6 meters per second. So a joule second, so let me do a joule second. This is a joule up here, so it's going to be a kilogram meter squared per second. So, because we lose a second from the second squared. Okay, so let's look at units. Seconds cancel, meters cancel, kilograms cancel, and we're left with 1 meter. So the dimensionality here is a meter. So then we put this in our calculators, and we have 6.626 times 10 to the minus 34. 34 divided by mass of the electron, divided by the velocity, 2.65, 6 E6. And we get 2.74 times 10 to the minus 10 meters equals 2.74 times 10 to the minus 10 meters. So that is about the size of half a hydrogen atom. So a hydrogen atom is about 0.5 times 10 to the minus 10 meters. So that's getting close to an atomic size. So that's an electron. What if instead of electron traveling that way, what if we put a Professor Ferguson at 118 kilograms going towards that? So let's see what my de Broglie wavelength is at that velocity. No, I don't want that. I want the entry. Okay, so let me do 118. Delete. There we go. All right. So the lambda MF, that's for Mike Ferguson. My de Broglie wavelength at that speed happens to be 2.11, actually 2.12 times 10 to the minus 42 meters. So that's a much smaller. The wave-like behavior of me is not that significant. The wave-like behavior of an electron, that's one of the reasons why electrons act so strangely, is because they're so unmassive. They're very, very light. So now let's do the switcheroo here. What is the velocity of an electron with a de Broglie wavelength of 1.2 times 10 minus 10 meters? So pause it if you want to work this on your own. So lambda d is h over momentum, and we want the that's a v. So that means then that velocity is h over m lambda d, 6.626 times 10 to the minus 34, all over 9.11 times 10 to the minus 31, divided by the wavelength, 1.2 times 10 to the minus 10. Okay, so let us go ahead and put that in. 6.626 e is 34. You might start to memorize these numbers as you go along and then promptly forget them. There's a quiz called the Nerd Factor quiz. If you this course hopefully will increase your nerd factor. That's the number of things that you have memorized. Like, how far do you know pi? I know it to 3.14159.256. That's as far as I know it. There's people that know it further. Okay, well, either way, here is, wait a second, what did I do here? Oh, I did a divide. No, that's right. Oh. They put the minus sign in front of the electron. Heisenberg's uncertainty principle. Heisenberg, you know, I've never met Heisenberg. Personally, he's probably a bit of a jerk. He and another one, Haber, he was a bit of a jerk too. They were scientists, and they I guess. Then again, we've had some pretty crazy scientists too. They worked a lot for the Nazis. Not that well, I don't know. The more I learn about Heisenberg, I guess the more I don't like him. But anyways, let's go back to the science. He has his uncertainty principle. I'll do one more side. I've been watching this show called Man in the High Castle, It's on Amazon Prime, and I binge watched the first 2 seasons. And they called the atomic bomb the Heisenberg device, which he might have been able to make an atomic bomb. So it's interesting with that. Anyways, well, that's a aside. Oh, another aside. If you like Star Trek, they have transporters in Star Trek. This is a problem with that their transporters can't deal with, so they call them the Heisenberg compensators. So the Heisenberg compensator is something. The hats off to that here. Anyways, the uncertainty principle is the change in position, x's position, and change in momentum is greater than or equal to Planck's constant over 4 pi. 4 pi being 3.14159, blah, 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 blah. Okay, so this means that you can only know something's position and momentum to a certain degree. So quantum mechanics has 7 dimensions. There are 3 position vectors, so length, width, and height. So where you're at, and then it's where you're going. So if you have a point here, we can describe the point where it is, and then the other 3-dimensional vectors is where it's going. You have a point here, is it going this way, that way, that way? So there are 3 dimensions describing where the point is going. So, or the mass, or whatever it is you're looking at. And the last one, of course, is time. But then, so 7 dimensions there in quantum mechanics. And when you're looking at something, you can only understand where it is or where it's going, so to a certain degree. So if you know exactly where something is, you have no idea where it's going. And if you know where it's going, you have no idea where it is. So, I mean, some of the old jokes with that. So Heisenberg was pulled over by police. The police officer says, "Sir, do you know how fast you're going?" He goes, "I know where I am." So, and the joke is, since he knows where he has no idea what his momentum is, and momentum is vast times velocity if he knows his mass. Like, ha 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 ha. Oh, yes. That's one thing with science. Our humor is pretty rough, isn't it? Okay, so uncertainty principle. And this is a real thing. The other thing with this is you can turn it into energy and time, so you can only know the energy and the time for a certain place. And with photons of light doing laser pulses, if you have really short laser pulses, the energy of the photon it's just everywhere. You can't tell the energy. And then in the same token, if you know exactly what your photon's energy is, you have no idea how long the laser pulse is. The time frame in that is you can't track it down where the time is. So we more often have very short laser pulses than we have very exact energy-wise. So, okay, so let's talk about classical trajectory. So this is us. We're shooting a cannon, shooting off cannonballs, and it's going, pew, and it follows a parabolic pathway. What about if we have a quantum tank shooting electrons? What happens is that there is a probability distribution. So it's not that we're not good enough. It's just that the electrons or whatever quantum particle that we're shooting we can't tell its position and we can't tell its momentum to an exact degree. Another way of looking at this is the strike zone of a baseball pitch, so that this is the strike zone here, and most of the pitches are in that area, but there's some around the outside. And that's one thing with electrons. Electrons can truly be in many places at once, and they can actually occupy the same space and same time as other electrons, which is kind of strange to us in a classical manner. Okay, go back to Erwin Schrödinger, one of my favorite guys. So remember that if you're in heaven, hang out with Schrödinger and do not hang out with Heisenberg, but go seek out Schrödinger. And his wave equation here, it's H psi equals E psi. So if you study more and more math, this is called the Hamiltonian operator. Psi, this pitchfork looking thing, that's known as the wave function. So what is an operator? I've listed 4 operators here to the right: plus, minus, multiply, divide. Those are operators. So if you say 1 plus 1, you are saying I am doing an operation on the number 1 such that I'm adding another number, this case happens to be 1, onto that other number. And that is my operation is addition. the Hamiltonian operator is operating on the wave function such that it spits out the energy levels of the electrons in the form they're called, well, you can form a matrix, which is a series of numbers, and the eigenvalues of that matrix are the energy levels of the electrons. So if you study more and more math, you can understand it a little better. And one of the operations you do is the integral from negative infinity to infinity of the wave function vector dot product with the complex conjugate of the wave function over d tau. That's all space. So dx, dy, dz, or polar coordinates or spherical coordinates, usually spherical coordinates. So again, if I'm talking gibberish, this is just more advanced math in this class. This is where it comes from. So if you go on and study more chemistry and some more physics and math, this is what you're going to do. You're going to be able to do this math and solve those equations. So what about for this class? We've solved it. The energy level for a hydrogen atom, so this is the solution to the Schrödinger wave equation. The energy level for the hydrogen atom is equal to the n, the quanta number. N is a number. It's 1 to infinity. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up into infinity, but whole number steps. So, and the energy is then, this is known as the Rydberg constant, 2.18 times 10 to the minus 18 joules, and 1 over the principal quantum number n squared. And a couple things with this, a free electron has 0 potential energy. So this is, we're picking a number as our reference, and we're picking a free electron. So a free electron with no motion at absolute 0 has 0 potential energy. I guess even moving, its potential energy is not necessarily in motion. So a free electron, unbound electron, has 0 potential energy. Then when electrons become bound to a nucleus, we say it has negative potential energy. And the reason why we do this is just to make the math easier, so we can relate it to how much energy it takes to rip the electron off. So if we related it to some other bound point, we'd have to relate it to 2 different values, and we'd end up doing the same calculation but twice. So we just make it easy and just say a free electron. So this will come important later. This solution here for the hydrogen atom will become important later. But let's talk about the quantum mechanical model. So I've already mentioned the principal quantum number n, and this epsilon in math terms means it's where it exists. So n exists as positive whole numbers, 1, 2, 3 integer steps up into infinity. Well, that's the other thing is when I start talking about quantum mechanics and quanta, we have to use, and I've mentioned this before with atoms and counting atoms, that we have to use discrete mathematics. So continuous mathematics, like when you see a function like y equals x squared, and then you have a graph, and there always exists a smaller point, that's not the way that the universe works. So at least in the structure of space-time and in the structure of atoms. So these only exist in specific quanta, specific packets of existence. Maybe you've heard of something called Zeno's paradox. So the idea is, okay, so here's me and here's the wall. If I go half the distance to the wall, then I go another half, half, I'll never reach the wall. That's not entirely true because space-time itself is quantized. So meaning if you have 2 points and so let's say I go half the distance to that point, half the distance, I'll never reach that point. Well, not entirely true, because space-time itself exists in only real specific points, and there's several proofs for that. And the simplest one is the fact that we go from point A to point B, that we can get there. If there's a little bit of space-time between that, and every time there's a little bit of space-time, it takes time to move there. And if there's an infinite amount of space-time, or at least an infinite digressions to it, you'll never be able to get anywhere. So that means that the answer to that is the universe itself has structure. So there's structure to the universe. There's structure to space-time, and there's also structure to atoms. So that's what we're going to talk about now. And molecules, if you go on. We don't talk too much about the energy level of molecules, but atoms also have structure, and that's the reason why I'm clapping, I can't push the electrons of my hand through my other hand because of the structure of the atoms. Because you're like, you just told me that electrons can be in the same space at the same time. Yes, they can, but then two electrons coming towards each other or bound in different atoms will still have forces that they exert on each other. So I'm not really touching my hands. I'm feeling the force, the repulsion force of the electrons is what gives it its structure, is what gives it the pushback. Okay, so let's build up the quantum mechanical model of the atom, and we have the principal quantum number, so whole numbers. And then we're going to have a new quantum number, the angular momentum quantum number. And we're going to call it L. L exists between 0, 1, 2, so on, integer steps up. Only positive integers, though, and 0. So, well, 0 is, I guess 0 and positive integers up to n minus 1. So, if our n is 1, our L has to be 0. If our n is 2, our L can be 1 or 0. If n is 3, L can be 2, 1, or 0. So 3 minus 1 is 2, so it can, and it's integer steps, so it can be 2, 1, or 0. And when L equals 0, we give that a value, we call that an s orbital. When L is 1, we call it a p orbital. When L is 2, we have as a d orbital. When L is 3, we have as an f orbital. So if you wonder what those terms mean, S stands for sharp, P stands for principal, D is diffuse, and F is fine. So those are old spectroscopy terms, but they carried over to the orbitals. S does not mean spherical, P does not mean perpendicular, it means sharp and principal, and D is diffuse, and F is fine. There's other orbitals as well, but we only really name the first 4, or at least we give them other letters. Okay, then the next quantum number is the magnetic quantum number, and that exists from minus L to minus L plus 1, integer steps through 0, 0 is included, integer steps up to positive L. So that means, so let's look at this. So if n equals 2, L can be 0 or 1, and if L is 0, m sub L has to be 0. If it's 1, it can be minus 1, 0, or 1. So that's where we're building up. And the last quantum number, I know that the textbook does not talk about this in this chapter, refers to it in the next chapter, but the last quantum number is the spin. The spin is the projection of the magnetic field of the electron or fermion. Electron is a fermion any given time. It's up or down. Well, it's really moving around. So like if you have an electron, its magnetic field, generally speaking, points in a certain direction. And later on we'll learn that you can occupy 2 electrons in an orbital. Does that mean that they align? The spins of an electron will align if you have a very strong magnetic field on the outside, like a superconductive magnet in an MRI machine, or if it's really cold. If it's really cold, you can get the electrons' spins to align all together. But that's very infrequently that way. Usually they're flying around all over the place. And if you have 2 electrons, they're just flying around in opposite directions. Okay, so the spin is either plus 1/2 or minus 1/2. And the definition of a fermion is a particle that has a spin that is a combination of 2 integer spins, or 2 integers, I'm sorry. The spin is a fraction of 2 integers, and that it's not an integer itself. I mean, so a photon has a spin of 1. You're like, well, I could describe that as 2 integers. I can put 2 over 2. So it's a fermion. Like, nope. It's 2 over 2 is equal to 1, which is an integer. 1/2 is the ratio of 1 and 2, and it's not an integer. So anything that can be described as an integer is a boson, and anything that can be described as a fraction of two integers that are not an integer itself are fermions. So what's important about fermions, electrons are fermions. Fermions state, the Pauli exclusion principle states, no two fermions may have the same set of set of quantum numbers in the same atom. And then, so different atoms, you can have quantum numbers in different atoms, but the two electrons in the same atom cannot have the same set of quantum numbers. And this is what gives matter structure. So photons are bosons. They do not, at least when, as far as we don't know about their structure internally, but if you have two photons, they can be in the same place, the same time, same spin. You can have as many as you want. You could turn the whole universe into photons and put it into one single point in space-time. That is totally fine. That's because they are all bosons. Fermions, on the other hand, cannot. So if you have two fermions together and you put two electrons in the same atom, one has to have a different set of quantum numbers than the other. And then the structure builds up, and that is where we get structure with matter. So matter has structure because of this, the Pauli exclusion principle. So, and there's also, you might read about some exotic states of matter. Maybe you've heard of something called a Bose-Einstein condensate. That's when certain types of matter are bosons. So we've seen that with ruthenium atoms. Actually, NASA just did this in space. They formed a Bose-Einstein condensate in space. It's really hard to do. You have to get very close to absolute zero to do it. But you can get bosons to be in the same place at the same time. It's a new exotic form of matter we're still studying. Okay, so let's look at the quantum numbers. So I know I've given you a very big overview, and I'm going to try and bring it back down to this class level. So what are the quantum numbers and names for the orbitals in the n equals 4 principal quantum numbers? How many n equals 4 orbitals exist? So if you studied the Bohr model, it's 2n squared. So, well, actually that's the number. It's going to be n squared orbitals. It's 16, but 2 in each, so 32. But we can look at this another way. Okay, so n equals 4. N equals 4. L can be equal to 0, 1, 2, and 3. If L is 0, m sub L has to be equal to 0. For 1, it can be minus 1, 0, or 1. 2, it can be minus 2, minus 1, 0, 1, and 2. For 3, it's minus 3, minus 2, minus 1, 0, 1, 2, and 3. How many do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Just like the count in Sesame Street. So we have 16 orbitals, and we can fit 32 electrons in that. And where we are getting at, which we'll learn in the next chapter, this is the s orbitals, these are the p orbitals, these are the d orbitals, and these are the f orbitals. Let's say, name them, okay, and names, okay. And this would be 4s, 4p, 4d, and 4f. So those are the different ones. And you can fit 2 electrons in each, and that's where you get the periodic table. So this is the s orbitals, these are the p orbitals, these are the d orbitals, and these are the f orbitals in the periodic table. We will get to that next chapter. Okay. So which set of so one of these is erroneous. So which set of quantum numbers is erroneous? So let's see here. Let's go to each one. If n is 3, L can be 0, 1, or 2. Being 0 is fine. If 0, this has to be ML has to be 0. That's fine. Look at B. If n equals 2, L can be 0, 1. L being 1 is fine. If L is 1, m sub L can be minus 1, 0, 1. Being minus 1 is fine. Okay, that's good. Okay, gone to C. N equals 1. L has to be 0. If L is 0, M sub L has to be 0. That's fine. D, n equals 4. That means L can be 0, 1, 2, or 3. Being 1 is fine. M sub L then can be minus 1, 0, or 1. Oh, we got something here. M sub L is minus 2. This doesn't work. This one is erroneous. So, but you're like, well, this one's 4, and we have an M sub L that's minus 2 in 2 locations here. Well, that's because if you look at the hierarchical rules, this L is 2 and this L is 3. This one here, the L is not, the L is 1. It can only be minus 1, 0, or 1. Okay. So then, which set of quantum numbers is erroneous? So you can look at this one and you'll find out it's D. Okay. Now, okay, excitation and relaxation. So, you know, one of my favorite TV shows is Game of Thrones. Hopefully you like that show. Well, it's up to you. If not, pick another TV show. Maybe you don't like TV. Maybe, I don't know. Pretend like you like TV in that case. So here is my television, and I'm having a Game of Thrones party, and in front of my TV I have this really sweet chair, lazy boy chair. I can put my feet up, I can just sprawl out. Behind that I have this couch that you have to sit up on, and then I've got some crappy wooden chairs behind that, and then I have standing room after that. So you're the first one of the party. Where do you sit? You sit in the lazy boy. Why? Because if I'm going to be watching a Game of Thrones marathon and it's going to take like 8 hours, I'm going to be as comfortable as I can. Okay, if that chair is taken up, I'm going to sit on the couch. Why? Because sitting on the couch, at least it's nice padded surface, and then the chairs, I don't want to stand, because stand takes energy. You know, what was even higher energy? If I'm doing jumping jacks, so this person's doing jumping jacks behind there. I don't want to do jumping jacks for 10 hours, or 8 hours, or how long a season is, right? So we as humans, we like to be as low energy as possible for as long as if we're going to be sitting there somewhere for a while, like we're going to be as low energy and comfortable as we can. And what happens, let's say that I'm sitting in the lazy boy and then I go, there we go. I get up and I go to the bathroom. What happens? Someone nabs my seat. And what happens when that person sits down? That person goes, I'm relaxed now. I've been standing for 4 hours. I finally get to put my feet up on this lazy boy. I'm going to relax. So, and I come back and I'm like, get out of my chair. And I push this person back out of my chair. Of course, that takes energy, right? So maybe you can kind of see where I'm going with this. We have the nucleus of the atom, and we have the 1s orbital, so really close to the nucleus, really low energy. Then we have the other energy levels. And you have an electron, I'm putting there. So electron is there. And the ground state, the lowest energy state, is there. It's sitting there right fat and close to the nucleus. If you can excite it, so you can excite the electron up. And what happens when the electron is excited? How do you excite an electron up? You can do it with light, so electromagnetic radiation. You can do it with a chemical reaction. You can do it with heat, so you burn something with high enough temperature, you'll excite the electrons. And so you can also do it with electronic discharge. So you can hit it with electricity, hit it with a lightning bolt, and you'll get electrons jumping up in energy. So you do that, you hit this electron with a lightning bolt, and what does it do? It will relax down. Well, it can go to various states here, and as it relaxes down, this is the same electron, so a big step, you get a violet photon. For a medium step, you get like a yellow photon, and for a tiny step, a red photon comes off. So the wavelength of light depends on how big the energy gap is. So for a big energy gap, there is a high frequency wavelength of light like violet. For a low jump, there is a long wavelength, low frequency like red, or sometimes even infrared. You can have very high jumps that are ultraviolet. So hydrogen atom has an UV one. Fluorescent lights, the way fluorescent lights work is that mercury metal, so there's mercury gas, actually it's not metal, but it's gas inside the tubes. You hit it with electricity, so electron bombardment excites up, lightning bolt, right? So lightning bolt excites up the mercury atoms and they decay down, and one of the transitions is an ultraviolet photon. Then it hits the phosphorus, and then the phosphorus then fluoresces from the ultraviolet photon. So fluorescent light. That is how a fluorescent light works. Okay, and this same picture as I'm showing is what I tried to explain. And we've learned about the Rydberg equation here, the hydrogen atom solution to the Schrödinger's wave equation there. And this is the spectrum for the hydrogen atom. So hydrogen atom here. This first one, the UV photon, this is known as the Lyman series, and the visible one is called the Balmer series. So we'll see this one. Hydrogen looks kind of like a hot pink. And why are we seeing hot pink and we don't see red, teal, and violet? It's because our eyes. Okay, so we're humans. We're not spectrometers. We have very good vision, but we're not spectrometers. I mean, like when we see something, it's kind of like, is it food? Will it eat me? Or is this, a friendly human that I want to have contact with? And so we make our decisions very quickly, like, oh, is that a spider that I need to smush or run away from, or a snake that I need to run away from? So we process colors very quickly and assess things very quickly in a very, I want to say organic, but although it's kind of digital in a very analog fashion, although we're more digital than we are analog. So our eyes can't discern this. Our brains just see the signal coming in and we lump it all to like, all right, that averages to hot pink. And that's what I'm going to tell my person that I'm seeing. I see hot pink. I don't see 3 different wavelengths. So, okay, so that's the spectrum there. But let's look at this and we'll calculate some things out. So determine the wavelength of light emitted when we have a transition from the n equals 6 to the n equals 5 orbital. So using this equation here, the change in energy, and so if you remember we had the En equation, we're just looking at, and then the delta En, this is just E final minus E initial. So, and that's where that equation comes from. And so let's do this, delta E, and it says the wavelength of light. So what we're going to get the E photon, and if E equals hc over lambda, and then that means that lambda equals hc over the E of the photon will then give us the wavelength. So that's where we're going here with this example. Okay, so let's do this. So delta E equal to the Rydberg constant times 1 over 5 squared minus 1 over 6 squared. And then that's going to be our E, and then we put it into here. So then our wavelength is going to be hc over minus the Rydberg constant, 1 over 25 minus 1 over 36. And we just put that in our calculators, which I will do now. Okay, hopefully I've done the pause correctly and I'm back. So if you look at this here, I've solved it and put in the numbers, and we get 7,460 nanometers. So this is infrared, we can't see it. Most humans cannot see under 800 nanometers. They say 700 nanometers is our red. I can see 800 nanometers. It's a really kind of dark brick red. I can see a little past 400 nanometers too. It's kind of a really light sort of lavender looking kind of color down to like 380-ish. So, anyways, we can't see that color. And if you look at these numbers here, so H is 6.626 times 10 to the minus 34, C is 3 times 10 to the 8. And then the Rydberg constant, this is times 10 to the minus 18. And then we have these terms, 1 over 25 minus 1 over 36. So, and these numbers here, so 1 over 25 is, I guess there isn't a minus sign here. I should get rid of that minus sign. So how do we put this? There's a minus sign there because the bound electrons have negative energy, right? So the energy going in is lower. Well, it's negative potential energy. It doesn't have negative energy per se. Just how we define is how we relate the energy to something. And also, so the big number, so 36, so 1 over 6 squared. So having a big number in the bottom will give you it's a smaller number. So 1 over 25 is bigger than 1 over 36 because the bigger number in the bottom means a smaller. What's smaller, 1 over 10 or 1 over a million? 1 over a million is smaller, right? So the denominator being small, being big makes the number smaller. So I always know, for me, I always see these numbers as, like, I check to make sure the math's right, and I've been in my mind, like, it has to be positive because the energy is positive. And this is how I put it in the calculator, like that, and now I made it to nanometers. Okay, so you try this one out as it goes. What is the energy of the photon emitted as it goes from the n equals 3 to n equals 1 level? So pause this if you want to try and do it on your own, but I will do this now. So a final, this is 1 minus 1/9. So this is 9/9 minus 1/9. So this is then this is 8/9. So 8/9 Rydberg is the energy of that photon. So that's how you do that one. Okay, and we mentioned if you take the orbital shapes, this is the psi squared, which is the integral from negative infinity to infinity of the wave function times the complex conjugate of the wave function times d tau. So that's integrated over all space. So if you study more and more about math, if you know what a complex number is, complex numbers deal with I, the imaginary number. So imaginary number, it's the square root of -1. And then you can have, or it's just the even root of some sort of negative value is where the imaginary numbers are. And if you have imaginary numbers with real numbers, so real numbers being not imaginary, meaning not like 4, that's a real number. That's a even root of a negative number. If you have those together, those are complex. And a complex conjugate is just, if one was, so 4 plus 3i, the complex conjugate is 4 minus 3i. And so math is a really good model, but it's not perfect. What I does, the imaginary number, it gives cyclic nature to our number system. So so I by itself, I squared is -1, I cubed is minus I to the 4th is 1, I to the 5th is I. So that the fact that I does that, it gives a cyclic nature to our number system. So that's all it really does. It's not necessarily a fault. It's just kind of how the model and the imperfect model then actually describes really important things in nature, the cyclic nature of things that can. Okay, so let's go back to the orbital shapes. And again, if I'm talking over your head, I apologize for that. I like to tell you what's going on coming in the future. If you continue to study science, I'm trying to inspire you to. I think this stuff is cool, but maybe you don't like it. But maybe it's too much. But I'm trying to also tell you what level is appropriate for this. Okay, so here is the s orbital, and this is the 1s orbital. And this is the density and it's probability density. And if you look at the probability density, it approaches infinity as you get towards the origin. But then if you look at the radial distribution of that, so where the electron actually is, so what's the difference here? So the probability density, this is just this is the vector dot product of the wave function with its complex conjugate. So that's the psi squared. That's this. Then you include the integrated overall space, and then you get something that looks like this. Let me zoom in on it. So it looks like it's a function that looks like this. Actually, no, it's concave. Sorry, it's concave up. It's like this. So it's all concave up, and I mean it's skinnier over here. That we actually do have it approach 0. There is a limit for the 1s. There's no node. There's no 0, but there's a limit that approaches 0 at the origin. Not actually ever reaches 0. That's a math term. I know it's kind of going towards Zeno's paradox stuff. Okay, so, but one of the things with the 1s orbital is that there is a small amount of electron density very close to the origin. And maybe you learned in high school or somewhere else that electrons are not in the nucleus of the atom. Well, guess what? Electrons are in the nucleus of the atom. They can be in the nucleus of the atom, just not very much. There is a small amount of electron density in the nucleus of the atom, especially, and of that, the 1s electron has the most. So, and because of this small electron density in the nucleus of the atom, the electronic energy levels are slightly different for different isotopes. So if you have heavy hydrogen, so deuterium, and protium hydrogen, light hydrogen, which is just a proton, the energy levels are close, but they're ever slightly so different, and that's due to the electron energy levels being in the nucleus. They're almost indiscernible. So, and they're really only noticeable for hydrogen. There are other types of fermions, so muons, for instance. Muons, they've done muonic atoms, and that's many times heavier than an electron, or I should say massive. They're much more massive than electrons. So that means that there's more density in the nucleus, and then the energy levels are quite different because of that density in the nucleus. So, and again, that's way above this course, but I think it's kind of cool. Okay, so nodes, and I mentioned nodes. The if you ever see someone take a jump rope and spin it around real fast, this is and you have a jump rope and you hook it to the wall and you can spin around. You get an N=1. If you whip it around really fast, you can get 2 nodes there, and this node is this area of 0 density. This is the wave-like behavior in an electron, and the nodes is equal to the n-1. So if you look at the 2s orbital, there is a node. There's an area of no electron density. So you have some density around the nucleus, and even a little bit in the nucleus, much less than the 1s orbital. But then you have density going out, where most of it. So let me zoom out. So you have really where the 2s electron tends to be is in this kind of area around there. But this is not the electron dancing around there. Where is the electron? The electron is occupying all this space at the same time. So that's where we get the uncertainty principle. We're uncertainty of the position, and the position kind of is in this area. Same idea, the 3s orbital. 3s orbital has 2 nodes, but it kind of hangs out more a little bit outside the nucleus. And this nature of the s orbitals to do this is known as a phenomenon called penetration. And that's important when it comes to energy levels, because this penetration effect changes the relative amounts of the relative energy levels and the shielding. So we'll talk about this a little bit more when it comes to when we're building up the electronic model of the atoms, the shielding effect of other electrons. and what the effect that penetration can have on that. Then we'll also talk about the Zeeman effect coming up. Okay, so here are the other shapes of the orbitals. So here is the p electrons, and p electrons actually do have a node. So the two p electrons have a node at the origin. So there is considerably less electron density in the nucleus of a p electron than an s electron. Here are the three p electrons. With the L equals 1, there's 3 m sub l's, and you have the 3 different ways. And for these p's, they orient themselves along the axes, and with a node at the origin. And so those are the shapes. And here are the d electrons. These are kind of fun. So you have here are the 3d orbitals, and you have, of these, the more important ones are this dz squared and the dx squared minus y squared. Why are those important? Because they align with the x, y, and z axes. And those are found preferentially in terms of bonding. So having bonding between metals and nonmetals tend to be there. You can have bonding over here. The book doesn't really talk about the signs of the wave functions. This is important for bonding. The signs, they have, these will have plus, well, anyways, the negative sign there, the donut, these show how the orbitals can bond with other form molecular orbitals, how they can, we'll talk more about bonding when we get there, but when 2 or more electrons approach each other in an atom, they will form new sets of orbitals, and then they will occupy those. And the possibility of them, in part, deals with the signs of their wave functions. And also, this dz orbital is kind of looks funny. There's something called the Jahn-Teller effect. That is where you get, and copper complexes do this, it has to do specifically with the shape of this dz squared orbital. They will elongate along they call it the azimuthal, the z-axis. They will go from an octahedral effect, it's complex, and then they will elongate and be a more prolate octahedral complex. That's called the Jahn-Teller effect, and like I said, that's from that dz orbital. And then there's a similar one for tetrahedral geometry called the Rayner-Teller effect. So that's something else you can learn about as you go on. And here are the f orbitals. These are all kind of funky looking, so these are kind of cool. Those are the 4f, I should say. These are the 4f orbitals. Oh, and they do talk about the phase, the plus and minus sign. Okay, so they do talk about the phase of the orbitals. And this, in part, is why atoms are spherical. So last thing, concept. So here is the s orbital. So here's one p orbital, here's the second p orbital, and then here's the other one. And then we got the dz. So let's see here. We got the xy plane, the xz plane, and then we got one more plane. Oh yeah, the xy. This one there, and then we got the x squared, y squared there. Then we've got the z squared, like that. So that's why atoms are kind of spherical. They're kind of a little lumpy in terms of their electron density, but they're pretty lumpy. And also, funny enough, that's kind of what nuclei look like too. So nuclei, protons and neutrons have energy levels just like electrons, but they're much further apart. So it makes the math easier. But yeah, that's, atoms are mostly spherical. And but yeah, I think this is a good place to stop. And I will see you when we talk about chapter 8. So goodbye for now.